Welcome to Lecture 6, the natural logarithm and exponential functions. Before I give you the motivation for this section, let me summarize what we've done so far with natural logs and exponential functions. So we defined the natural log of x. We've defined it abstractly as this, or maybe even better if I say concretely, as this integral. As this integral right here. So this is a function. This is a perfectly good integral. And then from here, we defined e to be the number so that, well, let me say natural log of e, which is 1 to the e of this is equal to 1. So e is that special number where this area under the curve is equal to 1. So from here, the fundamental theorem of calculus tells us that the natural log of x has an inverse function, and it's not hard to show that the inverse, so that the natural log of x and e to the x are inverse functions. And here I'm assuming x is greater than 0. So e to the x is defined for all x. It's not the case that natural log of x is defined for all x. So we're just focused on x greater than 0 here. Okay, so natural log of x and e to the x are inverse functions. So let me ask you this question. This sounds silly at first, but what is b to the x? So for concretely, what is the function 2 to the x? Now that seems like a silly question. If x is equal to 2 or 4, 3, or any integer, you know how to answer that. If x is equal to any rational number, you know how to use that using powers and roots. But what if x is equal to, oh, I don't know, cube root of 3, or pi to the 5th, or something silly like that? How do you even define that? So we can actually define 2 to the x or b to the x using our only the exponential function. So let me start with a question that I'm sure you've probably asked at some point, and I know I asked when I first took calculus. How does one differentiate b to the x? Like 2 to the x. Why is that not in the back of the book in your derivative integral table? Well, for some books it is, but for a brief table, that's usually not in there. Just e to the x is. And, well, first of all, let me even ask you a more basic question. How do you even define b to the x? So this is to realize that b to the x, now you can even use this as a definition, is the definition of b to the x is just e to the natural log of b to the x, which is just e to the natural log of b times x. And that we know how to define for all x. I don't care if x is transcendental, irrational, irrational, whatnot. Assuming here that x is, we're assuming that x is greater than 0. Okay, so the derivative of b to the x, you probably saw this in your first semester calculus, equal to the derivative of e to the natural log of b times x. And so this is my, you know how to take the derivative of e to the kx. Remember, just the k pulls down. So here's our quote-unquote k. And now this thing highlighted in red turns back into b to the x. So in summary, taking the derivative of an exponential function, you get the same function, but a natural log of b pulls out in front. Notice if b, in the special case where b equals e, this is just 1. So we get our familiar rule that the derivative of e to the x is e to the x. Okay, so now that we've defined the natural log, and we know it has an inverse function, and now that we've defined b to the x in terms of this inverse function, we can define for any b greater than 0 and not equal to 1, I guess b could, I think b could probably be equal to 1. Let's say it's not equal to 1. We might run into trouble. Yeah, so log base p of x is defined to be the inverse function of b to the x. So e to the x and natural log are inverse functions. So let's define log base b to be the inverse function of b to the x. So that means that if y is equal to log base b of x, b to the y equals x. So to sketch this, see if I have room here. Yeah, I can squeeze this in here. So this here, so this function is y equals log base b of x, and this is 1, and these are inverse functions, so so if this is the line y equals x, then function y equals b of x is just the reflection. This function is the reflection across the line y equals x. So these two are inverse functions. Okay, so to summarize, we define the natural log of x. We use that to define e to the x. We use that to define b to the x for some other base b. And now we go backwards and say we use that to define log base b of x. These are inverse functions of each other. Okay, so let's list some properties of log base b function. These and all of their details of the derivations are listed in the book, and there's many other, or I guess a handful of other properties as well. I don't think it's necessary to list every slight variation, and I also don't think it's necessary to list every single derivation. I encourage you to look at the book if you are interested in any of these. I will summarize them, and also notice that I am going to handwrite the right-hand side because I encourage you to try to predict what I'm going to write over here before I actually do. It's good practice, and if you need to, pause the video and try to figure it out, and then play the video to see if you're right. Okay, so this first one, b to the log base b of x, b to the x and log base b are inverse functions, so this is going to be equal to x, and this is for x greater than 0. Because if x is less than 0, the log function is not defined. Okay, for the second one, it's similar. Again, log base b and b to the x are inverse functions. So this is going to be equal to x. Although here we get a little bit lucky. B to the x is always greater than 0, so this is always defined even if x is negative. So this holds for x. I guess I hadn't talked about how to I'm going to say x in negative infinity to infinity. So this is the in sign. This is a member of. So x is about this for x, all real values of x. I guess I didn't really talk about b to the x where x is negative, but that's not hard to do. You just take the reciprocal once you have it for b positive, for x positive. Okay, the third one, log base b of x. You might remember this from high school. This is a really useful little property. This is equal to the natural log of x divided by the natural log of b, or really any base. You can replace this with any base. Natural log is the most convenient one. And this holds as long as b is not equal to 1, because we don't want this denominator to be 0. Okay, so the next property, I did this on the last slide, but let me just summarize again. The derivative of b to the x is the natural log of b times b to the x. And this, of course, holds for all x, positive, negative, or 0. Well, because of that, the integral of b to the x is 1 over natural log of b times b to the x. Of course, we need plus c here. And here I'm assuming b is greater than 0 and b is not equal to 1. Because if b were equal to 1, we'd be dividing by 0 here. And if b equals 1, you know how to compute this integral, right? That just becomes integral of 1 dx. Okay, next property. The derivative of log base b of x. Well, how do you do this? Well, you just write log base b of x as natural log of x over natural log of b. And now natural log of b is a constant, so you can pull that out. And you get 1 over natural log of b times the derivative of natural log of x, which is 1 over x. So you get 1 over x natural log of b. And of course here I'm assuming that x is greater than 0 because, well, I guess x can be anything here, but I'm assuming x has to start greater than 0. So if you want to do this for x less than 0, you make this absolute value, you can do the same thing. So the derivative of log base b of absolute value of x is going to be 1 over x natural log of b, and here x can be positive or negative. We better actually say that x is not equal to 0, otherwise we're going to get some, this is not going to be differentiable. We're going to have some corner happening at x equals 0, or we likely will. So let's just be safe and say that x is not equal to 0.